Morning, and this is a hard keynote to follow if you were here on the last session. I do not have 50 years of work to show you today, but what I hope to show you is a prototype system that we've been working on called Collaborative Spatial Streaming, and it's sort of all inspired by, of course, something where a lot of us are working on. The fact that applications are increasing across the board for 3D and to in AR, VR, and to use these applications well, we need 3D content. So whether that be photogrammetry, live 3D capture, or some Gaussian splats, as Andrew showed earlier, we need 3D content, and there's a bunch of different applications. Just to show a few more here that I'm uniquely interested in. This is a video for follow-up from a talk last year we had from our friends at Canon, where they had 40 cameras situated around the Cleveland Cavaliers stadium and did a reconstruction of the basketball game as it was occurring, which allowed them to produce some really cool 3D visualizations with the raw 3D reconstructions. So if what we can take away here is that we have live performance in a way, captured from, in this case, 40+ perspectives composed into a static or dynamic 3D scene, but a singular scene. And so as we think about systems like this, I want to walk back and consider how we might compose them, leading up to what I'm going to be talking about. So if we consider a general 3D capture system, I want to first consider single device capture systems. So it could be anything like my phone or a standard RGBD camera. But in a single device capture system, of course, this is comprised of a single imaging system. The benefit of this is that you have greater accessibility and simplified system complexity. However, these single device capture systems often suffer from missing data. If I look at you with my single capture system, I cannot guarantee that you have a back of your head. You probably do, but I can't see that with my imaging system. However, if you stay still, I can walk around you and begin to see your back, and that's how things like photogrammetry work. These limitations of the single device capture systems can also be overcome with modern machine learning techniques that attempt to infer these novel viewpoints or fill in missing data. So here we see my persona within the Apple Vision Pro, and obviously while I'm wearing a VR headset, the headset cannot capture my face, but there are sensors in the device and models running with that data to try to fill in the 3D from my head. Okay, single capture system, good for accessibility, but we're missing some data. Let's expand. Let's go to a multi-device capture system. Again, the whole point we're talking about this is we want to capture a bunch of data from many different perspectives and put it together into a unified 3D scene. So these multi-device capture systems obviously use multiple imaging devices, be it 2D and or 3D. And we see this example from Microsoft's holoportation work. There's actually like 24 cameras situated around the scene that are capturing, some of them are composed into 3D imaging devices, and then those are used to capture the subject within and reconstruct the geometry. And then in this example, the two sides are being captured and transmitted to one another, enabling a real-time 3D communication system. Similar to the follow-up work from Google, Project Starline, where two users can converse in real time and in natural 3D. These systems are nice. They obviously improve the scene coverage in detail by composing multiple perspectives and viewpoints. However, they rely on precise static calibration. In other words, all these cameras in these systems need to be calibrated together into a unified system, which is, if you've done it, kind of a cumbersome process. And if you add a device or an imaging system, or remove a device or move a device, you potentially have to recalibrate the entire system. You've changed the structure of it and the relationship between the cameras, and you need to put Humpty Dumpty back together again, which is not fun. But it's possible, obviously. We can achieve some very high fidelity systems. So I want to show one other example that's really driving the inspiration behind this work. and that is something like remote robotics. It's not the only application, but this is a driving motivation where you have a bunch of dynamic environments and dynamic imaging systems. So we see from this clip, we have moving robots that are traversing challenging environments. Eventually we'll see a drone flying around. And the challenge here is we have these mobile imaging systems, but we want to take the data from all of them and put them into a unified coordinate system in real time. We don't want to capture all the data and go back and run some optimization and figure out all the relationships between the cameras. We want to build something like this, where all the sensors and cameras know where each other are in real time. So to do this, let's look real quick at calibration. So a lot of us are familiar with a traditional pinhole model here, but this is going to be important for where we're building. In a traditional imaging system, we can assume that each independent imaging device operates within its own coordinate system. Each camera is its own view of the world. And 3D points in the real world are going to fall onto camera pixels. And we can see in the image on the right, there's this point in the real world, XYZ, that goes through some lens and then onto the imaging plane. And there are some parameters that govern this transformation. And this is a simplified model, but these parameters, of course, through these calibration procedures can be estimated. For our purposes, we need to understand that we need extrinsic parameters, which govern the position and orientation of the imaging device with relation to the world system. And we need the intrinsic parameters, how the 3D world is projected onto the imaging plane. And if this is newer, I like to think of it like this. If I have a point in the 3D world and I have my imaging device, I need to know the rotation and translation. So maybe I rotate to align, and then I translate it to get it the point to the camera. And then the point will fall through the lens and fall onto the 2D imaging plane from there, governed by the intrinsics of the lens. So that's all fine and dandy. We have a single imaging system model here that relates 3D points to a single 2D image or sensing plane. With multi-device calibration, the goal is then to determine the spatial relationships between all devices in the system. And this is what those systems I showed earlier with 20 cameras, let's say, this is what has to be solved for all of those. We need to know how all the cameras are spatially oriented to one another, such that you can integrate data from each device into a single unified 3D reconstruction. And these calibration procedures are usually accomplished through an outside-in imaging approach. Normally we wouldn't call it that necessarily in the context of calibration, but it's going to be an important distinction coming up. And that said, so we have some calibration target here at the bottom, and what we want to do is have our fixed external sensors around the volume, look at that board, and determine from that board all of the sensors' relationships to it. So in other words, we see this world point XYZ will fall on a particular pixel on this camera and a particular pixel on this camera. And if I can know the relationship between these two cameras, namely the rotation and translation, I can unify and determine that this is the same world point and put all of the pieces of the puzzle together. We can see that better, maybe, in this visualization. As I mentioned, with independent imaging devices, each device is its own source of truth. It's its own origin. So we see device 1 here has its own origin, device 2, device 3. What we can achieve through calibration is, of course, putting them all into the same coordinate system, and now they all are part of this world space. Now, this is great. This is pretty traditional multi-device calibration, but for my purposes, or for our purposes, for the motivating example, this is, some limitations are that it's a static system in the sense that, again, I can't move cameras around. And if I want to add a camera or remove a camera or, again, move a camera, I don't really have that flexibility. I have to rerun this calibration process. So what I'm proposing here is a kind of, I wouldn't even call it a novel method. It's just kind of a unique approach where we're going to overcome these limitations with a two-step process, this dynamic multi-device coordinate system. And it's a two-step process composed of an initial alignment step where we acquire an initial common reference point. Again, we're going to use this calibration board as an example. And then we're going to have this live dynamic tracking after the calibration step or after this alignment step. So here's our imaging system as it begins. We have a bunch of devices sort of in their own coordinate spaces. If we point them all at the same target here, we can have them agree that this target is the world origin. This target is 0, 0, 0, let's say, and all of these devices will know where they are relative to this point. Now, here comes the dynamic tracking part, is if we can track each camera in its own frame of reference, so notice this is t equals 0. If we go forward in time, let's say, the devices all start to move around. This is what normally breaks the calibration. I don't know where one device is to another any longer. But in this system, we do. So even as this device, turns around and starts walking away, this device backs up, this one stays pretty much stationary, they all have a fixed reference point to where they started. So this initial alignment, we use an outside-in approach. Again, each camera just finds the target and essentially puts a pin through it, and that's 0, 0, 0. This implicitly aligns all of the device's coordinate systems. And then we have the dynamic tracking after that, which uses both feature recognition and motion tracking to determine where the device moves in its local space. And this tracks the device's motion relative to these local features. And I'll show you an example of this. So as we see a device with such features turn on here, as we walk through, in this case, my living room, we can see a map of the world being built up, and we see that it's persistent. It knows where the geometry is, and it sort of stays fixed in the space. This is not necessarily novel technology, but this is useful for our purposes. Such that as this device here, for example, starts walking away, we can continuously know where it's at in this space. So this is useful because now we can start to implement this. So we have a collaborative spatial streaming system. It's built on iOS devices using ARKit. By building on ARKit, we know all the device intrinsic parameters, just sort of inherent to the device itself provided by the operating system. It uses outside-in image tracking for that initial alignment and inside-out world tracking for the dynamic extrinsic estimation. We use then the LiDAR sensor on the iPhone and iPad devices to give us a 3D image, which we can then transmit along with the intrinsic and extrinsic parameters. The main point here is that for each packet of data, we can recompute XYZ in world space. So putting this all together, we got kind of a late start, but I'm trying to hurry because we want to keep us on time here. In our collaborative spatial streaming system, we have N devices. In this case, iOS devices, so we can use a LiDAR. We send all the data to a centralized server, and we forward that to a web-based visualization environment. In this case, we're building this on Three.js. It's a 3D library for the web. Supports desktop, mobile, WebXR, 3D displays, for example, the looking glass display. So we can output this 3D content on a variety of devices, or we can send the 3D content from one device to another. So we can do many to one or many to many. The result is something like this. So from the single device, in this case, we can identify this target and then capture 3D data, again coming from the LiDAR on the back of the iOS device. And we see on the right-hand side here we have the 3D geometry of the scene and a reference of where the device is in world space. The device, again, is no longer its own world origin. This point here, for example, is the world origin. Where this obviously becomes useful is with multiple devices. So in this example, we have two devices, both currently seeing this fiducial marker, and we have the first-person view for both devices. And it might be kind of hard to see with this point cloud rendering, but we see both devices in their, in this new world space, sort of automatically aligned by having seen this target first. My favorite example here is one that wouldn't be possible with a single device. Here's my daughter capturing my wife. This is me capturing her, and she's capturing her. But if you've done any sort of RGBD imagery, we can see that from the single perspective, of course, she casts quite a wide shadow. From this device's perspective only, maybe I have no idea that there's another person here. But with this secondary auxiliary perspective, all coordinated and aligned in this world space, an external observer, a third person, can see all of this with a bird's eye view. This is kind of a work in progress. This is kind of not the best visualization. It's kind of hard to get your head wrapped around it, but what we see here is a shared environment, and you can see in the bottom right multiple devices sort of coordinating in this 3D scanning. And as all of us move around the scene, of course our unique perspectives are changing, but we're all composing this shared reconstruction. And if I were to turn around and walk out of the room, because this device is tracking itself essentially after that initial alignment, the coordinate system stays global. I still belong to that shared coordinate system. Again, this is very useful for these types of applications where you have many devices roaming about and collecting a lot of data, and you need to put them all together into a shared perspective. So, lots I could say more on this, but in the sake of time, of course, there's more work to do. We can add some color and validate to the alignment. We have systems that we've already proposed for real-time, low-bandwidth 3D streaming. So those things will be incorporated. And then, of course, exploring all the various fun and exciting applications that could come of this. So with that, if you have any other questions, you can come find me, but I'll take a few if we have any time.
Okay, thank you.